So, good evening, Clydesdale. It's a pleasure to be back here, even virtually, to talk to you once again. So this is the end of everything. As you can see from the subtitle, I'm going to be talking about the fate of the Earth and the Sun and the galaxy, and ultimately the fate of the universe. So I'll be giving a short prologue and then talking about the future of the Earth and the Sun and the solar system, the far future, looking at stars and galaxies, and ultimately looking at the far, 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 far future and the fate of the universe. So as not to finish on too depressing a note, I'm going to wrap up with a slightly more upbeat epilogue. So that's what I'm talking about this evening. So the story so far, this particular talk is a bookend to a talk I've given before about the beginning of everything. And I'm not going to cover everything in that talk. Let me just recap what that says. The universe began 13.8 billion years ago. Everything that we currently see in the observable universe, in other words, all of the trillions of galaxies within a sphere some 100 billion light years in diameter, all of those objects used to be a lot closer together. And if you wind the clock back far enough, everything used to be separated by no more than centimeters. The universe ever since then has been expanding. In the first few minutes of the universe made lots of neutrons and lots of protons, which eventually became the atoms of hydrogen and helium that we see in the universe today. So this talk is not about the origin of the universe, it's about where we go from here 13.8 billion years after its creation. And in order to make sense of what I'm talking about, I'm going to use this timeline running across the top of the screen. Each of these boxes represents a time 10 times further into the future. In other words, we're going to be looking at 10 to the power 1, 10 to the power 2, 10 to the power 3 years into the future, 1,000 years. 10 to the 4, 10 to the 5, 10 to the 6, or 1 million years into the future. 10 to the 7, 10 to the 8, 10 to the 9, a billion years into the future. And similarly 10, 11, 10 to the 12, a trillion years into the future. So this red box is going to be moving across the top so that we can sort of keep track of where we are. Otherwise, these ridiculous times into the future are a little bit difficult to keep track of. I'm indebted to the work of Adams and Laughlin, who wrote a paper some 25 years ago in which they laid out the timescales on which many astrophysical phenomena are likely to occur. And I've used that paper as a way of trying to get all my slides in the right order. I'm not going to deal with it topic by topic. I'm going to deal with it strictly in time moving forward. So it might jump around a bit between the Earth and the Sun and the galaxy, but I'm always moving in chronological order. So I'm not going to start after 100 years or 1,000 years. Let's assume that we don't blow ourselves up. Let's assume that we get climate change under control. One of the things that we can predict with some accuracy is the way the Earth's spin is changing. The Earth's axis is precessing, like the diagram on the left-hand side, and the Earth's axis points to a big circle in the sky, and it traces that circle once every 26,000 years. So that's why we've highlighted 10 to the 4 in the red box at the top there. We're on timescales of order 10 to 20,000 years. And if we see the direction of the Earth's axis mapping out onto the sky, we see that at the moment the Earth's axis is pointing close to the star Polaris. That is currently our North Star. In another 10,000 years or so, because of precession, the Earth's axis is going to point in a completely different direction and will be pointing in the direction of Vega. So Vega will become our North Star. Some people seem to think that the North Star should be the brightest star in the sky. Well, in 10,000 years it will be, making life very easy for Boy Scouts trying to define the direction of north. But what's the real consequence of changing the pole star? Well, at the moment, we are nearer to the Sun, perihelion, because of the elliptical orbit of the Earth around the Sun. We are actually closest to the Sun in January during northern winter. But if the Earth's axis is pointing the other way, then we'll be closest to the Sun during northern summer. which means the effect of distance from the sun and the effect of tilt towards or away from the sun will exacerbate the seasons. The seasons will become a little more exaggerated because the hottest time of year will be when we are closest to the sun rather than furthest from the sun. So these variations in the Earth's climate are predictable because of changes to the Earth's spin. And similarly, we can predict changes to the Earth's orbit around the sun, and these collectively are called Milankovitch cycles. And I'll be mentioning that one more time in the next few slides. On a timescale of 10 to the 5 years, voyagers are expected to pass nearby stars. If you remember, the Voyager probes Voyager 1 and Voyager 2 were launched in the late 1970s. Voyager 1 passed Jupiter and Saturn. Voyager 2 used a slingshot to get from Jupiter to Saturn and then Uranus and Neptune. So these two Voyagers are heading out of the solar system. At the top there, Voyager 1 is going to pass the star Gliese 445 on a timescale somewhere between 10 and 100,000 years, somewhere of order probably 30 or 40,000 years or so. Voyager 2 is heading out in a different direction, and that is going to pass close to the star Ross 248. Now, Pioneer 10 and Pioneer 11, also shown on this slide, they were launched earlier in the early 70s, but they are travelling more slowly, so they won't reach the stars on quite the same timescale. Pioneer 10 on the right there is heading off in the direction of Aldebaran, and Pioneer 11 on the left is heading off in the direction of the centre of the galaxy. Still on a timescale of 100,000 years into the future, we're expecting repeating cycles of glacial and interglacial periods, in other words, ice ages and the periods between ice ages. The historical record of the Earth tells us that we've been through ice ages roughly every 100,000 years or so. And given that the Earth entered a warm period, an interglacial period, relatively recently, we're expecting the next ice age on that sort of timescale, 100,000 years or so. Why are the ice ages relatively predictable? Well, it's another manifestation of Milankovitch cycles. In other words, it's the way the Earth orbits the Sun, changes to the Earth's orbit as it goes around the Sun. I'm not going to say anything more, but if you go and look up Milankovitch, you'll find all about these things. Still on a timescale of 100,000 years into the future, we know that the Earth is slowing down, and in a separate talk I talk about how we add leap seconds to keep our clocks synchronized with the rotation of the Earth. Adding leap seconds is analogous to adding a leap day every 4 years to keep our calendars synchronized with the seasons. But if the Earth continues to slow down the way we predict, then leap seconds would need to be introduced not every few years as they are at the moment. We haven't actually added a leap second for quite a few years now. We would need to add a leap second every day. In other words, at this particular point, 100,000 years into the future, we expect the moon to have slowed the Earth down to the point where a day is not 24 hours long, but 24 hours and 1 second. So the final minute of the day would be not 60 seconds long, but 61 seconds long. Still on a timescale of 100,000 years, we can't predict when stars are going to go supernova. But looking at certain stars, like heavy stars like Antares or Betelgeuse, or in this case Eta Carinae, we would expect at least one of these stars to have gone supernova on the timescale of order 100,000 years. We can't predict these things particularly well. Like earthquakes, we know they're going to happen, but we can't predict when. But we think on a 100,000 year timescale, Eta Carinae would probably have gone. If you look at it now, this image shows a Hubble Space Telescope picture of a planetary nebula that's being formed because the outer layers of Eta Carinae are being sloughed off. It looks like the star is unstable to the point where it's already ejecting a lot of material into space. So perhaps this is the prime candidate to go supernova. It isn't just supernova that we have to worry about. For instance, Wolf-Rayet 104 is 7,000 light years away, but its death may result in radiation that's even more powerful than a supernova. That's because this system has a very high rate of rotation, which produces jets via a mechanism that we don't really fully understand. But if, when this star dies, the radiation produced in these jets, if those jets happen to point towards the Earth, that could be a serious problem for us, even at a distance of 7,000 light years. You may think that's far enough away not to be a problem, but even at that distance, if the jet happens to be pointing towards Earth, that could give us a very severe dose of gamma rays, perhaps even enough to end life on Earth. Moving forward now to 1 million years into the future. We know how stars are moving in the Milky Way because, for instance, spacecraft like Gaia are able to map the positions and the velocities of stars very accurately. And hence we can work out how we are moving around the Milky Way and also how some of our neighbours are moving around the Milky Way, all on independent orbits, but every once in a while we may happen to get close to another star. And that's been predicted for a star called Gliese 710. That is going to pass very close to us and then drift away again. It looks like a very odd orbit, but remember we are both orbiting around the centre of the Milky Way. So Gliese 710 is actually going to come within a distance of us that takes it inside the Oort cloud. And almost certainly that will result in disruption of lots of particles within the Oort cloud. Lots of these icy bodies are going to be disrupted by the passage of Gliese 710, and almost certainly a large number of objects are going to come raining down into the inner solar system. It's been calculated that we might expect to see naked-eye comets perhaps every few weeks for a period of maybe 1 million years or so. It's interesting to note that for a little while our solar system will actually have 2 suns, just like other places we know about. Still on a timescale of 1 million years into the future. This picture is not supposed to indicate that we're expecting an impact like this meteor crater in Arizona. We're not expecting this once every million years or so. The picture reminds us, well, 2 things. One, wasn't it lucky that this impact just missed the visitor centre there? Okay. And the other thing it reminds us that any impact on the Earth will get eroded by weathering. So this impact might have only been tens of thousands of years ago, but any older craters would have been almost eradicated by the effects of wind and rain and temperature changes. The weathering that we see within the Earth's atmosphere effectively eradicates any evidence of very old meteor impacts. So you might say, yes, that happens on the Earth, of course, due to weathering, but we wouldn't expect it anywhere else. So, for instance, the footprints on the moon will last forever. Well, actually, no. It's not weathering in the sense we understand on Earth, but it's space weathering. The moon is constantly bombarded with micrometeorites, which means Aldrin's footprint there will end up getting eradicated because the micrometeorite impact is effectively stirring up the regolith and effectively redistributing all of the particles. Even the pieces of metal, even the lunar lander and the lunar rover that are sitting on various Apollo landing sites, even they will end up getting eroded, and effectively no evidence will remain if you wait long enough because of the micrometeorite impact. Moving to 10 to the 7 years into the future. We can look at Pioneer 10. We said that it would be passing other star systems in somewhere between 10 and 100,000 years or so. So in 10 to the 7 years, we would expect it to have already passed through perhaps hundreds of solar systems. It's moving at a speed that would probably take it into a solar system, and if it doesn't get picked up by any civilization living there, it will exit those solar systems at a similar speed. So it might have passed through hundreds of solar systems. And the plaque on Pioneer 10, if anybody picks it up, will tell them where it came from. It'll tell them who we are, our size relative to the spacecraft. The pulsar map on the left tells them where we came from, and the little cartoon at the bottom says that we came from the third rock from the sun, or the probe was launched from the third rock from the sun. But on a timescale of 10 to the 7 years, the passage of Pioneer 10 through the interstellar medium will be such that micrometeorite impacts of the plaque with whatever dust exists in the interstellar medium will mean that the plaque becomes totally eroded. So if Pioneer 10 gets picked up in the first 100 or so solar systems, then the people who pick it up will be able to read the plaque. But if it doesn't get picked up in 100 solar systems, if it continues through the Milky Way, after this sort of time period, anybody that does pick up the space probe will not be able to read the plaque, and so will not be able to tell the history of this particular spacecraft. If we move forward to 10 to the 8 years in the future, we can ask ourselves about the fate of Saturn's rings in the next 100 million years. But it helps to think first of where Saturn's rings actually came from. It is thought that perhaps a moon, perhaps Mimas, might have made Saturn's rings. If a moon became pulverized and produced a lot of dust, that might have formed Saturn's rings, and maybe some of that dust recoagulated into a moon such as Mimas. When you look at Mimas and its huge crater, you might think to yourself,
that's no moon, it's a space station.
Because it does seem rather odd. But calculations have been done, simulations have been done to see, is it possible if we take a moon such as Mimas and smash it to pieces, could we explain the existence of Saturn's rings? And that has been done in this particular simulation. So we're taking this small moon here and we're going to assume it gets pulverized by perhaps collision with another moon or perhaps with an incoming comet. If we pulverize the moon and then let nature take its course, what do we expect to happen? The simulation shows this. After a matter of only hours or just a few days, most of the debris is spread around the planet. You might think if you pulverize a moon, maybe it will end up as a cloud of debris which orbits Saturn for quite a while. But in fact, the interaction of all the individual particles in the debris field start to spread out. And after only a couple of weeks, we have an identifiable ring system. And looking at the way the ring particles behave now, we realize that they're all interacting with each other and interacting with the other moons of Saturn. And all of the ring particles are slowly spiraling closer and closer to the planet and eventually raining down onto the surface of the planet itself. So over millions of years, this debris field will produce the rings that we see today. So we think the rings are many millions of years old, perhaps 10, 100 or so million years old. But it means that the processes that made the rings are ongoing. So in other words, if we move forward millions of years into the future, the ring particles will continue to spiral inwards and rain down on the surface of the planet, which means on these timescales, Saturn will lose its rings. A rather sad state of affairs. So for those of you who like looking at Saturn through a telescope, make the most of it. They're not going to be here forever. Still on a timescale of 10 to the 8, 100 million years or so, we can sometimes fool ourselves into thinking that by looking at an orrery, we pretend that the solar system is sort of clockwork, either an orrery or a tellurian, which shows the Earth, Moon, Sun system in a little more detail. We wind these things up or we make them move with motors, and we fool ourselves into thinking that if we know where the planets are now and we know how fast they're moving, we can work out where they're going to be in the future. Well, that's fine for 100 years, 1,000 years, tens of thousands of years into the future, no problem. We could wind the clock backwards and ask ourselves, where was Jupiter, where was Venus 2,000 years ago? Could that explain the Star of Bethlehem, for instance? That's not a problem. But on these timescales of order 100 million years or so, the solar system is chaotic. We cannot predict where the planets are going to be. Not only that, we can't even predict whether or not a given planet will still be in the solar system. It could be that Jupiter decides to eject one or two other planets. We think there have been major rearrangements of the solar system in the past, and there might be rearrangements of the solar system in the future. So don't let the appearance of an orrery fool you into thinking we can predict on arbitrary long timescales. Staying with 10 to the 8 years, 100 million years or so, that's roughly the length of time it takes the Milky Way to rotate once. So we are here indicated by the yellow dot. On a timescale of 10 to the 8 years, the Milky Way is going to rotate, and the Sun, it is calculated, will move from a relatively low density area, which is where we are at the moment, in between spiral arms. The Sun is going to move into a spiral arm where the number of stellar neighbours we are expected to have will be significantly higher. So in a high density region, we expect to have many more stellar neighbours. At the moment, we have a few stellar neighbours within 4 or 5 or 6 light years. When we move into a spiral arm, we might expect to have many, many more. What are the consequences of having lots of stellar neighbours? Well, one of them we've already thought about, and that is when another star gets close to us, it can disturb the Oort cloud and send lots of comets or asteroids our way. Well, we think that has happened in the past. If we look at how many species have become extinct as a function of time, with present day on the right going backwards in time as we move to the left, we see that there have been spikes in terms of extinctions of various species. The most recent one labelled on the right hand side there, 65 million years ago, the so-called KT, the boundary between the Cretaceous and the Tertiary eras, that's the impact that killed the dinosaurs. So if we associate each of these extinctions with the arrival of asteroids or comets that impact the Earth and significantly change our climate, you can see that we expect to get this, well, we would expect to get an extinction level event a few times every few 100 million years. So very roughly speaking, they come round every 100 million years or so. And it's thought that that's due to the fact that we would have a lot more stellar neighbours when we move into one of the spiral arms of the Milky Way. So this artist's impression is a rather fanciful idea of what we can expect. A huge rock coming our way. If we look at what it's heading towards on the left-hand side, it seems to be heading for Italy, as best we can tell. Well, that's bad news for Italy, but of course, if it's a large enough rock, it'll be bad news for the rest of the Earth. A large enough incoming asteroid or comet will result in species being exterminated. Whether or not that includes us, well, it's almost impossible to guess. If we have a lot of near neighbours, not only will that disrupt the Oort cloud and send asteroids our way, if we have lots of nearer neighbours, then maybe one of them could go supernova. At the moment, there are no stars particularly close to us that are candidates for supernova. The nearest ones are many hundreds of light years away, some of them thousands of light years. But if we have a lot more neighbours in 100 million years' time, it is possible that some of those neighbours might be supernova candidates. A supernova within 100 light years would be a danger to Earth, it has been calculated. And certainly a supernova less than 20 light years from us would be very dangerous. It might even end all life on Earth. Nearby supernovas have occurred in the past. Supernovae within 100 light years, for instance, will leave deposits of a particular isotope called iron-60 in Earth's sediments. Iron-60 doesn't occur naturally, but it is generated in a supernova. And iron-60 is radioactive, which means it changes from iron into something else over a period of many millions of years. Iron changes into cobalt, which then changes into nickel. What that means is, if we look in Earth's sediments and we find traces of this particular isotope, iron-60, given that it decays into nickel after a few million years, any we do find can't have been there for very long. It is not an isotope left over from the formation of the Earth billions of years ago. That would not exist anymore. So the existence of this particular isotope tells us that we have had supernovae within perhaps 100 light years of the Earth in the historical record. It's happened before, it will probably happen again. On a timescale of 10 to the 8, the moon is continuing to slow the Earth down. Through tidal friction, the moon is effectively robbing the angular momentum of the Earth, and as a consequence, the moon is getting further away from the Earth, increasing its angular momentum. So it's an exchange of angular momentum from one body to the other. At this particular point, 100 million years into the future, the moon will have slowed the Earth down to the point where the Earth is now revolving not once in 24 hours, but once in approximately 25 hours. Perhaps this is the point at which we switch to a decimal version of a clock. But the consequence is that the moon will move further away. As well as slowing down the Earth, the moon will move away from the Earth. We can measure it at the moment. It's moving away a few centimetres or so every year. But before too long, the moon will be so far from the Earth that it will be impossible to have a total eclipse of the sun. At the moment, the disk of the moon is large enough because of the proximity of the moon to cover the disk of the sun. But if the moon moves much further away, the disk of the moon will no longer be large enough to completely cover the disk of the sun, and so we can only expect to get partial or annual eclipses in the future. So for those of you who like eclipse chasing, again, make the most of it while you can. But perhaps a more important consequence of the moon moving away from the Earth, apart from the lack of that particular spectacle, is that the moon has a stabilising influence on the tilt of the Earth's axis. The historical record tells us that the tilt of the Earth has been about 23.5 degrees, give or take a degree, for quite a long time. The cartoon on the left gives you an idea of the sort of variation, barely 1 degree either side of 23.5 degrees. And of course it's the tilt of the Earth, the 23.5, that determines the seasons in the northern and southern hemisphere. If the moon moves much further away from the Earth, it will find it difficult to stabilise the Earth's axis, which means the Earth's axial tilt could change erratically. It could go vertical, it could go horizontal, and that of course would result in wild climatic changes. So on a timescale of order 1 billion years, we can expect the Earth's climate to change radically. Still on a timescale of 1 billion years into the future, we can think about the fate of Voyager. We said that Voyager would pass nearby stars in 10 to 100,000 years. So what does this mean at 10 to the 9 years? Well, Voyager is carrying a gold disk. Strictly, it's a copper disk plated in gold, but it's still called a gold disk. And it's thought that that gold disk should survive for approximately 1 billion years. Gold is a very stable element. And why would this survive longer than, for instance, the plaque on the Pioneer space probes, which only lasted perhaps 10 to the 7 years? Well, the gold disk on Voyagers will last longer because the disk on the right here is underneath a protective cover on the left. And that will become pitted, but the gold disk should survive substantially longer than the Pioneer plaque. So, unfortunately, even though the gold disc will survive, containing various recordings of people on Earth, it's a bit of a shame that the the cover on the left, that is going to get pitted and eroded by Voyager's passage through the interstellar medium, and it's the cover on the left that contains the instructions for actually playing the record on the right. So, after 1 billion years or so, the Voyager space probe will have moved through, I don't know how many tens of thousands of solar systems. If it's not picked up after tens of thousands of solar systems, then if it is ever found, it might well be that the people who find it will not be able to figure out how to extract the information from the gold disk. So let's hope some civilization in the first 10 or 20 or 30,000 solar systems that Voyager travels through, let's hope it gets picked up before the gold disk is unreadable. Still on a timescale of order 1 billion years into the future. The Sun hasn't yet reached its red giant phase. It doesn't get there until about 5 billion years or so. But on the way towards becoming a red giant, the Sun will increase its luminosity. It's been calculated that it might increase by perhaps 10% for every billion years. So the Sun's luminosity increases. That means the Earth is going to get hotter. And perhaps the greenhouse effect will drive the surface of the Earth to a very balmy 80 degrees Celsius, effectively boiling off the oceans and giving us a bit of a problem. We're going to have to decide whether we try and stay on Earth or whether we leave Earth and come back when it's cooled off a bit. The Sun will expand into a red giant, And if we think of the size of a red giant, it's comparable to the orbit of the Earth. And so you can imagine the surface of a red giant getting uncomfortably close to the Earth, and yes, this could be a problem for us. But it's not actually a given that the Earth will be engulfed by the Sun. Yes, it can be calculated that when the Sun expands to become a red giant, it will end up with a radius comparable to the radius of the Earth's orbit. But another thing you have to take into account is that as the Sun expands into a red giant, it will produce very strong solar winds. A lot of mass will be lost from the surface of the Sun. With less gravity pulling on it, that means the Earth's orbit is going to change. The Earth will effectively move away from the Sun. So this cartoon on the left tells us what might happen. As the Sun expands, the Earth will move further away from the Sun because it will be losing mass. So the Sun will continue to expand, and eventually it will probably end up larger than the Earth's orbit, or at least the orbit where the Earth used to be. Along the way, the Earth might end up in a new orbit, perhaps roughly where Mars is now. So it's possible the Earth might survive and might not get engulfed by the Sun. It's a rather tricky calculation to do, to take into account all the possible effects, but at the moment the jury is still out. Once the Sun has gone through its red giant phase, the Sun will become a white dwarf many billions of years into the future. A white dwarf is essentially a lump of carbon. Whether it's carbon or whether the pressures are high enough at the core to be diamond, well, we don't really know. But the Earth will have problems even once we've got past the point at which the Sun has expanded to a red giant and then eventually sloughed off its outer layers into a planetary nebula, leaving the white dwarf behind. And that is because the Earth is going to lose its magnetic field. At the moment, the Earth has a magnetic field because it has a liquid core, and a liquid core spinning is effectively a dynamo that generates a magnetic field. But the Earth's core is cooling. It's nothing to do with radiation from the Sun, it's purely an internal effect. Radioactive decay of elements for the last how many billions of years have been keeping the core of the Earth molten. But on this timescale of order 10 or so billion years into the future, the Earth's core will have cooled down because of the radioactive decay of the various elements. They will no longer be enough to keep the core molten. The core of the Earth will solidify. We will no longer have a dynamo, and we'll no longer have a magnetic field, which means we'll then be exposed to the radiation, perhaps not so much from the Sun, but certainly from cosmic rays. It is thought that this is probably what happened to Mars. Mars is a smaller planet, so its core would have cooled down faster, and once the core of Mars solidified, Mars would have lost its magnetic field and perhaps as a consequence lost its atmosphere. So in a sense we'll be behind Mars by quite a few billion years, but eventually we will suffer the same fate. If that wasn't enough, surviving the Sun going through a red giant phase and then perhaps surviving the loss of a magnetic field, just when we thought it was safe, then we realised that we're going to collide with Andromeda. The Andromeda galaxy is currently 2.5 million light years away, but we can measure its relative velocity and we see that it's heading towards the Milky Way. The mutual gravitational attraction of these two galaxies is pulling them together. And on timescales of a few billion years, 3, 4, 5, 6 billion years or so into the future, the Andromeda galaxy is going to collide with the Milky Way, and there will be a riot of new star formation. On a timescale of 4 to 5 billion years, they will probably pass through each other. It's unlikely that any of the stars will collide. When two galaxies pass through each other, a lot of the gas and a lot of the dust will collide, but individual stars are very concentrated and very dilute in the Milky Way and in the Andromeda galaxy, even though there might be hundreds of billions of stars. If you think of the distance between stars, it's unlikely that any two stars will collide with each other. So the galaxies will probably pass through each other and then settle down to make one mega galaxy. This shows what it might look like after 5 billion years. We've lost the spiral arms of the Milky Way and the Andromeda galaxy. It looks like we might have two nuclei here. the supermassive black hole at the centre of the Milky Way and the supermassive black hole at the centre of Andromeda might stay separate for a little while, but eventually they will merge as well, and we'll have one mega, probably elliptical galaxy when both galaxies lose their spiral arms. But this won't be apocalyptic, in the sense that it might be the sun survives, it might be the sun gets pulled out of the Milky Way by the tidal effects of another galaxy passing through. But even if the sun does get ripped out of the Milky Way, it'll take millions of years to happen, and the planets, whatever planets exist around the sun at that time, will simply go with it. So one way or another, if the Earth still exists, the sun will probably survive the collision with Andromeda, and we will survive with the sun. On a timescale of 10 to the 11, the interaction between the moon and the Earth has finally come to an end. One day is now equal to 1 month. The length of time it takes the Earth to spin once on its axis, a day, is now the same as the length of time it takes the moon to go around the Earth, 1 month. The Earth is now tidally locked to the moon. In other words, the same face of the Earth always faces the moon. So if you were on one continent on Earth, you would always have the moon in your sky. It would not rise, it would not set, it would always be in the same place in your sky. And if you were on perhaps another continent on the other side of the Earth, you would never see the moon. It would never rise above your horizon. So the idea of one face of the Earth always facing the moon is just mirroring, of course, what the moon has been doing for billions of years, where we're only seeing one face of the moon. At this point, 10 to the 11 years into the future, the Earth and the moon will be tidally locked to each other in much the same way that Pluto and Charon are tidally locked to each other, always with the same face facing each other. We're now moving to 10 to the 12 years into the future, 1 trillion years into the future. If we look at what's going on around the Milky Way, we know the Milky Way is surrounded by lots of smaller galaxies, lots of little satellite galaxies, like, for instance, the Large and Small Magellanic Clouds, but also dozens, if not hundreds, of others. The Milky Way will not only collide with the Andromeda Galaxy and ultimately M33, the Triangulum Galaxy. Effectively, the entire local group, all of the galaxies shown in this picture, will end up collapsing into one mega galaxy. It won't actually be a spiral, that's just a symbolic notation there. So all of the galaxies get eaten up by this one cannibalistic large galaxy. What's going on for more distant galaxies? Well, if you remember the talk from, a couple of years ago, I said that even though galaxies are receding from us faster than the speed of light, it is still possible to image them. You can do that with a camera, even without a telescope, and the Hubble Space Telescope on the right-hand side here has been imaging deep field and ultra-deep field, and a lot of these galaxies are receding from us faster than the speed of light, but we can still image them. But if you go 10 to the 12 years into the future, if you take the expansion of the universe and follow the conclusion of what happens if that expansion continues, and as far as we know continues to accelerate, that means that none of our neighbouring galaxies will be visible. They will all be too far away from us to be visible. Light will not have had time to reach us from these very distant galaxies, simply because the expansion of the universe will carry them too far away. So that means that any civilization that comes into being 1 trillion years from now, if they build themselves a Hubble Space Telescope and they look out into the universe to see what the universe is made of, they will see nothing other than the stars in their own galaxy. So these two stars are in the Milky Way. That's what the Hubble saw, as well as thousands of more distant galaxies. But in 10 to the 12 years' time, no matter what technology a civilization may have, if they look out into the universe, they will not see any galaxies other than the one in which they live. They will come to the conclusion that the entire universe is simply their own galaxy. And that's a very sobering thought, to realise that we live at the moment in a privileged time where we are able to see these trillions of galaxies that are out there. It won't always be the case. Now, I said right at the start of this talk that in the beginning of everything, the universe made a lot of protons and neutrons, which made hydrogen and helium, but we're not worried too much about the helium. We're thinking about the protons, which are the hydrogen. It took about 3 minutes for that process to happen. In other words, after the Big Bang, 3 minutes later, all of the hydrogen that's going to be powering all of the stars was made. But after 1 trillion years or so, it's starting to run out. Now, just as an aside, some people have hypothesized, well, maybe it's possible to make stars out of something other than hydrogen. Some people disagree. A lot of people say you really do need the lightest element to start with. You can't simply start making stars out of heavier stuff. But some people have hypothesized, well, maybe it is possible. Maybe it's possible to have fusion reactions in the core of a star made with heavier elements, and maybe the surface temperature will be a lot lower than the sort of stars we're used to. A red giant might have a surface temperature of just 3000 Kelvin or so. Maybe it's possible to make a star with a surface temperature 10 times lower than that. Maybe only a few hundred Kelvin. That would mean the surface of the star might be cold enough for ice to form. Frozen stars. Well, it's only hypothetical. If that's the picture you've got in your head, by the way, that's Disney's version of a frozen star. That's not what I'm talking about. If that's the picture in your head, let it go, because what we're talking about is a fusion reaction with ice in the atmosphere of a star. It's a pretty amazing idea, but it is just a hypothesis. There's no evidence for these things. So if we really do need hydrogen to make stars, then what does the future look like? I'm going to go beyond 10 to the 12, but I need to change gears, otherwise we'll be here all night. So now each box is not 10 times further into the future, but is now 1,000,000 times further into the future than the previous box. So if you forget the idea of making stars out of heavy stuff, if you assume that we need hydrogen, then we can ask ourselves, what happens when all the hydrogen has run out? Stars live a long time, but they don't live forever. The age of starlight will come to an end. There will be a time when there are no more stars shining. The stars don't shine anymore, but they will continue to orbit their galaxies. The dead stars are left drifting like zombies. There will be white dwarfs like our sun. There will be neutron stars. There will be black holes. There are no nuclear reactions keeping white dwarfs white. In other words, they start hot, but they will cool down, and they will end up as just not a bright piece of carbon. They will end up as a dark piece of carbon. Eventually, they will become black dwarfs. Some stars will be ejected from the Milky Way, and those that aren't ejected from the Milky Way will be eaten by the central supermassive black hole. We think that magnetic fields will funnel all of the matter of the galaxy into the central supermassive black hole. For instance, in this particular case, the magnetic fields in a distant galaxy have been mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy. That's the infrared telescope in the back of a 747, which unfortunately has been recently decommissioned. But it's thought that by mapping out these magnetic fields, we get an idea of how matter will end up getting funneled into the supermassive black hole. That's how they effectively feed. Now, what's going to happen to all the atoms in the universe? We know that the positive charge in the nucleus of an atom comes from protons. But we don't know what happens to protons in the long term. If protons decay, then all atoms will fall apart. But we don't know if protons do decay or not, and if they do, we don't know the timescale on which they decay. It's unlikely to be less than 10 to the power 36 years, otherwise we would have seen some evidence of it. So it's probably sometime beyond 10 to the 36. But even if atoms do survive beyond that particular point, then atoms won't survive much longer, because even black dwarfs will eventually evaporate, and when they evaporate there will be no atoms left in the universe. Remember, we will still have neutron stars and we will still have black holes, but in neither case are they made of atoms. So at this particular point in the far, far future, there will be no atoms left in the universe. Black holes will merge together. We know that galaxies have been colliding, and when they do, the black holes at the centres of galaxies will eventually merge. It takes quite a while, but we would expect all black holes to start merging with each other and grow as they do. So we won't have black holes like the one at the centre of our Milky Way with a mere 1 or 2 or 3 or 4 million solar masses. The black holes will grow until they are billions of solar masses, or perhaps trillions of solar masses, as galaxies continue to merge with each other. A slow process, but we are talking about the far, far, far future here. Even black holes are not eternal. It is thought that black holes evaporate, providing that you wait for a really long time. So why do black holes evaporate? Let's just take a quick aside. It is thought that the rules of quantum mechanics allow for energy to be borrowed effectively from nothing and then create particles and antiparticles, create matter and antimatter, as long as whatever you make annihilates and pays back the energy on a very short time scale. In other words, you can borrow energy, make stuff, the stuff annihilates, and you get the energy back again. That, we think, happens all the time. It's allowed according to the laws of physics that we understand. Stephen Hawking said, what would happen if that process occurred right at the event horizon of a black hole? What if we got matter and antimatter, or a particle and an antiparticle, created just outside a black hole? So we can imagine that as the event horizon. We borrow some energy, make some stuff, and look what happens. One of the two particles or antiparticles falls into the black hole, but the other one doesn't. And so from the outside, it looks like something has come out of the black hole. Strictly, it's come from just outside the event horizon. But Hawking calculated that there would be a flux of radiation away from all black holes, and eventually this came to be called Hawking radiation. The radiation increases with smaller mass, so in other words, as black holes get smaller and smaller and smaller, they evaporate faster and faster and faster. And that means the radiation levels of a black hole increase, and there's a sort of avalanche effect. As it gets smaller and smaller, the radiation gets faster and faster and stronger until the black hole evaporates in a flash of radiation. Even the supermassive black holes, it's easy to see that small black holes evaporate quickly, but even the supermassive black holes, the ones lurking at the centres of galaxies now, will eventually evaporate, though it will take trillions of times longer than the sort of black holes that we're used to, stellar mass black holes, the black holes that would occur at the end of a star's life, end of a massive star's life. But the length of time that would take, you see the red box has now reached the end there of 10 to the power 84. I think we can dispense with that timeline now, because we're now getting to ridiculous numbers. 10 to the power 100 is a googol. Not that Google, that's just a misspelling of a Google. 10 to the power 100 is a googol. And after a googol years, it's been calculated that the last black hole, regardless of how massive it started out, the last black hole will have evaporated. So that means there is no matter left in the universe at all. There's just some radiation. And as the universe continues to expand, that radiation is going to get stretched to longer and longer and longer wavelengths. As there is no matter left in the universe, nothing interesting happens. And so you could argue that time becomes essentially meaningless. We measure time by the motion of something. When there's nothing out there other than radiation, the concept of time passing becomes almost meaningless. 10 to the power 100 years is a ridiculous time into the future. And I don't normally write out numbers with zeros, but let me just remind you what 10 to the power 100 actually looks like. 10,000 million, etc., etc., etc. It is a ridiculously long time, but it is possible to calculate what happens on these timescales, and that's why we believe this is the timescale on which the universe effectively comes to an end. It's a long time, or as Woody Allen would say, eternity is a very long time, especially towards the end. But another way of looking at these ridiculous timescales and trying to relate it to human timescales, well, the cartoon XKCD came up with a very nice quote. A human is a system for converting dust billions of years ago into dust billions of years from now, via a roundabout process, which involves checking email a lot. I thought that was a nice perspective on how humans fit into this timeline. But rather than leave you on too depressing a note, let me finish with a little epilogue. We live in a golden age. The sun is middle-aged and well-behaved and will be so for billions of years. The moon is at just the right distance to stabilise the Earth's axis and to stabilise the seasons. And as a byproduct, it gives us the spectacle of a total solar eclipse every now and again. Thanks to evolution, we are able to explore and discover and understand the universe around us. We can do that by building space probes to visit our closest neighbours, or we can build ourselves telescopes and look out into the universe and realise that there are trillions of galaxies at distances of billions of light years. But humankind could not have arisen in the very early universe. We needed a sequence of generations of stars. We needed some stars to take hydrogen and make helium, and then stars to take helium and make carbon, and then fuse carbon into other elements so that we end up with a universe that's full of carbon and nitrogen and oxygen and calcium and phosphorus and iron and all the other elements that we need to make us. And as we've just seen, the future, trillions of years from now, the universe is going to be very dark and very boring. So you could say the best time to exist is now. Thank you for listening.